In this video, we're going to talk about thin layer chromatography, or TLC for short. By the end of this video, you should be able to explain the principles of TLC as a qualitative separation method, perform TLC for a chemical reaction, and interpret the results. Let's say you have done a new reaction and you're not entirely sure when the reaction is going to be completed. How can you check the progress of the reaction? Or, let's say you have gotten your product but want to know if there are any side products or unreacted starting materials present. How can you test that? Well, TLC is one method to help you out. It is a qualitative method based on polarity to help us visualize what is going on in the reaction mixture. Similar to other chromatography techniques, TLC has one stationary phase and a mobile phase. The stationary phase is a plate coated with silica gel. Important points to remember about silica gel is that it is polar and can hydrogen bond to compounds. The mobile phase is a solvent or a mixture of solvents which has to be determined based on trial and error if it is an unknown reaction. We only use a small amount of solvent and pour it in a glassware, usually a beaker. This is referred to as the developing chamber. So let's see how this works. We're going to use a beaker as our developing chamber in this example. First, pour the mobile phase into the beaker so that it is about 0.5 to 1 centimeters deep. Next, put a watch glass on it or use a parafilm so the beaker is filled with the solvent vapors. Meanwhile, draw a line with pencil on a TLC plate a few millimeters to about 1 centimeter above the plate. The line must sit above the solvent when put in the beaker. You can test this with an empty beaker first. Next, use a capillary tube to spot a small amount of reaction mixture right here on the line. Put the plate into the beaker and put a watch glass on top of beaker. The solvent will rise up to the plate due to capillary action. As the solvent moves, the reaction mixture will also move up. Once the solvent reaches almost the top, remove the plate and use a pencil to draw a line right here. The distance that the solvent has traveled is called the solvent front. Always remove the plate before the solvent reaches the top of the plate. Now, most compounds appear white, so we need a way to visualize the spots on the silica plate. The most common visualization technique is the use of a UV lamp. This works mostly for aromatic groups and highly conjugated compounds. There are other visualization techniques such as dipping the plate in various chemical solutions depending on what we have in the reaction mixture. In this example, we can see two spots, spot A and spot B. Why is that? Well, the different compounds in the reaction mixture will not travel at the same rate, and they will separate as they travel up the plate. Remember we said that silica is polar. Knowing that, which compound do you think is more polar? Compound A is going to be the more polar one because polar molecules like interacting with other polar molecules. They have similar physical properties and so they like hanging out with each other. Thus, compound A travels more slowly on the plate. Similarly, you are more likely to hang out with people who share similar characteristics with you. On the other hand, compound B is less polar and has a weaker interaction with silica gel, so it is going to travel faster and move further up the plate. So then, based on this TLC plate, we know we have two different compounds in our reaction mixture and we know their relative polarities. Now let's calculate the RF values or retention factors. This is just the ratio of the distance the spot has traveled to the distance the solvent has traveled. We use a ruler to measure the distance. In this example, the solvent has traveled 5 centimeters, spot A has traveled 2 centimeters, and spot B has traveled 3.5 centimeters. Thus, the RF values are as shown. Nonpolar compounds such as aromatics or alkenes have higher RF values as they travel further up the plate because they have weaker interactions with silica gel. Polar molecules, on the other hand, have lower RF values as they have stronger interaction with silica gel and move slowly. Polar molecules that can hydrogen bond, such as alcohols and carboxylic acids, have really low RF values because they can hydrogen bond with the silica gel. Let's go over a few examples. Here, we're going to spot the starting material. If the starting material is solid, we need to first dissolve a bit of it in an appropriate solvent. Next to it, we're going to spot the reaction mixture as well. Once we take out the plate, this is what we have. Based on RF values, we can see these two spots have the same RF values. What does that tell you? Well, this tells you that you probably have some unreacted starting material in your reaction mixture, which could be because either it was used in excess or the reaction has not gone to completion yet. If we also know the expected product and if we have a sample of the product, we can also spot the product to determine if the reaction has been successful or not. For example, here we have a spot with the same RF value as the product. This could indicate that the product has been formed. There are no spots with the same RF value as the starting material, so there's probably no more starting material left. However, there's another spot showing up here. This could be either a side product, a byproduct, or an intermediate, which we could either determine based on the reaction or we need to do further analysis. Here are a few tips for successful TLC analysis. 1. Make sure to use pencil to draw the line. If you use pen, the ink will also travel up the plate. 2. The line on TLC plate must sit above the solvent in developing chamber. 3. Make sure to use a watch glass or parafilm on top of the developing chamber. 4. The TLC plate must stand straight in the chamber. Otherwise, the spots will travel at an angle and you won't be able to distinguish them. So let's review quickly. TLC is a qualitative method to help us visualize what we have in our reaction mixture. It works based on polarity. Polar molecules won't travel as far up the plate, whereas non-polar molecules travel faster and move further up the plate. And this is how we can separate them. Thank you for watching.